This is the next video in a chapter on atoms, molecules, and ions. We have just finished covering chemical symbols, and we're not quite ready to talk about molecules with multiple atoms, but we are going to start seeing them, and we'll need to know how to talk about them and how to draw them. So we're going to do a quick sidebar and introduce chemical formulas. So there are some compounds that have more than one atom in them, and those are called molecules. The smallest unit of a compound that contains multiple atoms is a molecule. And there are several different ways that we can draw or represent molecules, depending on what sort of information we want to convey. So the first and simplest way we can represent a molecule is by writing the condensed version, which is called a molecular formula. And these are the sorts of things you've seen before. We're going to use methane as an example. So when we write the molecular formula for methane, we simply write the chemical symbol for carbon and the chemical symbol for hydrogen with a subscript 4 to indicate that there are 4 hydrogen atoms in this molecule and 1 carbon atom in this molecule. So the C and the H are chemical symbols for 2 different elements. And then the subscript numbers tell us about the number of that type of element in a molecule. And you'll also notice that there's a 4 subscript next to the hydrogen, but there isn't a subscript next to the carbon. And that is because there is just 1 carbon atom in this molecule. So when we write a molecular formula, if there is only 1 atom of something in a molecule, we omit that 1. So this is the smallest, most condensed form of representing a molecule, but it gives us the least amount of information. So we have some other tools in our toolbox that we can use to represent these molecules in different ways. So the one you will probably find the most useful a little bit later in this course is called the structural formula. And like its name suggests, it shows more about the molecule's structure or how the atoms are connected. So if we want to know how the hydrogens are arranged around the carbon, we would use a structural formula by indicating their location and connecting each of the atoms to its neighbors using a line that represents the bond holding those 2 atoms together. So in a structural formula, the bonds show how atoms are connected. And this is valuable information. The arrangement in space is something we like to know about. Now, these are very straightforward. These 2 models only use the chemical symbols. They simply arrange them in different ways. We have 2 other ways of representing molecules, and these look more like pictures that you could draw with shapes in them. The first kind is called a ball and stick model, because if you were to physically build a representation of this molecule that you could hold in your hand, spherical shaped balls and linear sticks would be used to connect the balls together to create this molecule. So we're going to draw what that model might look like on our paper. So we'll have circles to represent each of the atoms, and we'll connect them with bonds again, but the lines are going to look a little bit different in this model to help us indicate which bonds are coming towards us and which bonds are going away from us in space. which is the benefit of this model. So the ball and stick model gives us accurate geometry. And geometry refers to the arrangement of the atoms in space. So in the structural formula, you might have thought that each of the hydrogen atoms was at a 90-degree angle to the hydrogen atom next to it, and that they were all sitting on a flat, planar shape. But we can see from this ball and stick model that the molecule actually takes up space in 3 dimensions. One of the hydrogens is coming towards us, one going away from us, and 2 in the plane of the page. So we will talk more about how to draw pictures like this in a few weeks, but for now, you can just recognize the benefits of this type of model. There is one more style of picture, and that is called the space filling model. And this is a model that is usually generated by software, but I will draw a picture here just so I can be clear about what it looks like. So the space filling model emphasizes the size of the different atoms and how closely they are to the other atoms. So I'll give it my best go. Ends up looking something like this. I can assure you it looks better when a computer draws the picture. But this sort of space filling model includes accurate atomic size information. It indicates that the hydrogen atoms are smaller than the carbons, and it tells us about how closely they're connected to that carbon atom. The ball and stick model makes it look like the hydrogens are really far away from that central carbon, and the space filling model shows us that they are actually very, very close together in space. So in our 4 models, pros and cons, molecular formula is obviously the smallest. You can type it on a keyboard, you can list it in a worksheet really easily, but it gives no other information about the molecule. The structural formula gives information about the connections. The ball and stick model gives information about the 3-dimensional geometry, and the space filling model gives information about the size of the different atoms. So those are reasons that you might choose those different models to represent a molecule. And now that we've talked about how to represent a molecule, there are a couple of molecules that I want to call your attention to while we are here. And those are 7 molecules that exist as what is called diatomics. So diatomics, that's a new word, and you can probably guess what it means. It has di, which means 2, and atoms inside of it. So diatomics are molecules containing 2 atoms. There are 7 of the elements that exist as 2 identical atoms connected together, rather than existing as individual atoms. Let me give you an example of that. So the element nitrogen, when found by itself, exists as a diatomic, an N2. So the elemental form of nitrogen is a diatomic. And here's an element that doesn't form a diatomic, carbon. Carbon's elemental form is just a single atom of carbon. One of the elemental forms anyway. Carbon happens to have several. So that's what a diatomic looks like. It has 2 of the same atom. There are 7 elements that exist in the form of a diatomic, and it's easy to remember what they are because the shape of all the diatomics in the periodic table looks like a 7. The 7 diatomic elements form the shape of a 7 in the periodic table. And so those atoms are going to be hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Almost didn't fit it, but we did. So these guys form a 7. Hydrogen is technically like at the way end of the 7. It isn't actually very close to nitrogen in the periodic table. You just have to think of it as the left end cap of the 7. So the 7 diatomic elements exist with 2 of the same atom connected together in its natural form. These are the skills you'll need to draw and represent molecules, and you can choose different forms depending on what sorts of information you would like to convey. And remember that when you see one of these 7 elements existing by itself, it will exist as a diatomic, as 2 of those elements bonded together